Good day, everyone. We are a team from Xiamen University, Malaysia. My name is Zheng Tianyue. Herein, we are honored to present our investigation on the application of silicon in photonics. With the rapid development of 5G optical and quantum communication, a more efficient chip has become the immediate need of nowadays society. As early as 1969, Mueller of Bell Labs first proposed the concept of integrated optics. In 1972, Semak and Yavoy proposed the idea of integrating optical and electrical devices on the same semiconductor substrate. This technology used optical waveguides to integrate a series of optoelectronic devices on the same substrate, thus constituting a miniature optical system with certain independent functions. At present, the technology to producing silicon become very comprehensive, and a silicon-based industry with strong capacity has been set up. Born with features of both microelectronics and optoelectronics, the silicon optical technology has become a hotspot for semiconductor and communications companies. So what makes silicon become the most popular element of this technology? There are 6 reasons. First, as you may know, to control the switching of transistor, semiconductors are necessary. With resistance between conductor and insulator, silicon has perfect construction that needed to transmit information. Second, as one of the semiconductor elements, the main driving force behind silicon's development is low-cost manufacturing. With the major processing after decades of development, we can already produce near-perfect silicon crystals in factories. It greatly reduces the cost. Third, the chemical and physical properties of silicon are very stable. Compared to the earliest semiconductor material, germanium, silicon can maintain stable at higher temperature and has a higher purity to ensure a better performance of the transistor. Moreover, silicon is non-toxic and non-hazardous, thereby having a widely and safe usage. Fifth, silicon is good optical material. It is almost completely transparent to light waves with wavelengths of 1.1 to 8 microns. This means that silicon optical chips can be directly applied to all optical communication devices and can be well adapted to existing standards. 6. The silicon-based platform has a high refractive index and optical confinement, which can reduce the optical waveguide width and band radius to 0.4 to 2 microns. With it, the integration density is expected to increase more than 100 times compared to the traditional chips, such as silicon dioxide-based and indium phosphide optical chips. This reduction of chip size also brings unique advantages, such as low cost, power consumption, and high speed.
My name is Gabriela Ivana Sugianto. So now I'm going to continue on what exactly is silicon photonics. So silicon photonics is a silicon-based optoelectronic mass integration technology whereby the protons and electrons are the information carriers. It is a fundamental support technology in some of the emerging companies such as big data, artificial intelligence, and future mobile communications. Silicon optical chips is one of the main application of silicon photonics, and it is an integrated optical circuits that integrates silicon optical materials and devices on the same silicon substrate through a standard semiconductor process. It mainly consists of modulators, detectors, passive waveguides devices, and etc. When we compare the traditional electrical chips with the silicon optical chips provides many advantages whereby it has high computing speed, lower power consumption, lower latency, and it undergoes non-extreme reductions in the process size as well as non-harsh manufacturing because it does not use the extreme ultraviolet lithography or EUV in the manufacturing process. According to Intel, the market growth rate for silicon photonics industry is predicted to be 40% and reaching $3.9 billion in 2024. And on the other hand, the current energy consumption in the digital industry based on integrated circuits is also increasing day by day and is expected to increase even more in the next 5 years. However, photonic chips is theoretically expected to reduce the energy consumption, achieving the goal of carbon neutrality. So silicon photonic chips nowadays can be used widely in optical communications within and between data centers and optical components. And today, data centers can connect switches that may be kilometers apart by using the silicon photonics technology. There's also an advances whereby the copper connection is replaced with the silicon photonics and has been proven to improve the speed of data transfer, and it is cheaper. And lastly, the photodiodes in existing silicon photonics optical transceivers rely on materials like germanium and indium phosphide to see light in the wavelengths used to move data.
Good day, Doctor. My name is Eugene Angelica, and here I will present on the advancements and improvement of the silicon photonic technology in the future. So the first advancement is called the heterogeneous silicon photonics. This is created by forming a heterogeneous integration between the silicon photonic and the 3,5 semiconductor, such as indium phosphide. And this technology has been proven by the Intel and also Juniper. The heterogeneous silicon photonics offers a way to separate the photon resonator and highly absorbing active media that can increase the quality factor of the traditional 3,5 semiconductor lasers. Furthermore, the line width of the heterogeneous integrated lasers are much narrower than the monolithic 3 to 5 lasers. And this narrow line width can potentially enable the DSP-free coherent links for telecom and datacom applications, which is expected to be a key enabler in next-generation silicon photonics applications. The second advancement is the photonic electronic integrated circuit. Silicon electronic is a good electron transfer material, and its combination with the photonic is expected to be used in high-speed data transmission during the 5 to 10 years. Furthermore, this integrated circuit can also be used in the manufacture of microrings, a flexible cavity device that can be used as lasers, modulator, and photodetector. However, the microrings are usually phase sensitive and suffer from photonic parameter instability. Majority of the microrings applications call for wavelength precisions of around 10 picometers. However, the lattice parameters of silicon only is 0.543 nanometers, and the wavelength granularity will be also the same amount even with atomic fabrication precision. So today's research found that the cavity stability issue can be effectively solved by the electronic photonic hybrid feedback. In addition, the resulting circuit is likely to perform better in all performance parameters once the stability problem is resolved.
Even with all the promising applications of silicon photonics, there are still several great challenges that delay the use of silicon photonics for the whole society. The first problem is the high price in the small market problem. The pre-existing silicon photonics is only for large data transfers only, and these are only applicable for large companies that have large processes. However, these large companies are also the ones who are able to afford the use of silicon photonics in their process. And to be able to commercialize the use of silicon photonics for the whole society, one of the solutions is by lowering the cost, and also by expanding the applications to sensors, signal processing, and imaging. And the other problem is the risk signals emitted by the silicon photonics. These risk signals cannot be easily incorporated into a usual electronic circuit model. Therefore, interfacing the electronic and the photonic domain simulators are one of the solutions for this problem. However, the effectiveness of this solution hasn't been proved yet. The third biggest challenges for the silicon photonics application is the high temperature dependency of the silicon photonics circuit. Slight changes over 0.1 Kelvin might detune the photonic waveguide components. The only solution is by knowing the physical configuration and also the heat distribution of each component of the silicon photonics, and also by using a very accurate thermal tuner that must correct the temperature changes every time there is a change in temperature. And the other problem is the mask layout of the photonics. Parasitic effect is a problem where the light doesn't end up to where it should be in the silicon photonics, due to the challenging placement of a complicated circuit on a single layer layout. However, for this problem, there is no proven solution yet. The bright future of silicon photonics application is hindered by the lack of standardization and scaling in silicon photonic chip design, mass production, and packaging, which results in the low production capacity, poor yield, and also the expensive cost of production. However, considering the amount of benefits the society might gain from the silicon photonics, more research is necessary to find the best solution for these problems. That's all for our presentation. Thank you for your attention.